Hi there and welcome to the screencast for Lab 6 for Biostats. So today we're looking at hypothesis tests with the petrels data. So I'm going to start by changing the author field there. And so this first code block is just reading in the data and doing some plots. So here we go. So we get two plots. We've got the difference in right wing length for the petrels between male and female. So we see that males are larger than the female by a little bit, and also differences by area. So we see that area E has the largest birds. Okay, and so next we're going to do a hypothesis test to test whether there's a difference between male and female directly. So this is exactly the same as was done in lecture 5. And so we'll run that, and so we can see that what it does is it estimates the average of the means, the mean of the females and the mean of the males, and you can see the difference between them is about 3.2 millimeters, and the confidence interval for that is between 5 and 1, and the p-value is 0.001. So what's our conclusion? So is that it is unlikely that our data that we'd see a difference of 3.2 millimeters by chance due to random sampling if there was no difference in the population. P equals 0.0015. So our data are not consistent with there being no difference between male and female right wing lengths. Our data suggests that the difference is around 3.2 millimeters, and we're 95% confident it's between 1.2 and 5.1 millimeters, with males larger on average than females. Okay, so what we're using is we're using the p-value to make a decision as to whether there's a difference or not. So our p-value here is small. Right, and because it's small, that suggests that our data are inconsistent with the hypothesis of no difference, which suggests that the difference is actually real, right? So our data is trying to tell us that the difference is real, and so our hypothesis test is, so we've got evidence against the hypothesis that there's no difference. And then the confidence interval can be used to quantify how big a difference it is. Okay, so actually the difference is actually fairly small in practice, right? These birds have wingspans of 750 millimeters on average, so that's 3/4 of a meter. It's about the same height as most tables, right? 750 millimeters. So the birds are quite big, and the difference between the male and females is only between 1 and 5 millimeters, which of course is very small. Okay, but nonetheless there is a difference. It's just quite small. Okay. What about between the areas? So we'll add another code block and we'll do the same thing, but between areas. So I'm copying and pasting the code in from the lab sheet. And so here we're checking whether there's a difference in between area A and area B. Okay. So what do we see here? So area A is just the area A birds. Okay, area B is just the area B birds because we've subsetted out just the area B birds. And so we're doing a test for, is there a difference between area A and area B? Okay. So you can see it's worked out the mean of the area A birds and the mean of the area B birds, and we see that the area A birds are larger than the area B birds, right, by about 6 units, isn't it? And the p-value is very, very small. So this is 2.2 times 10 to the power of minus 12. So this is, essentially 11 zeros point, 11 zeros, and then a 2. So it's really, really tiny. Okay, so our data are super inconsistent. With the hypothesis of no difference in mean right wing length between area A and area B birds, as the p-value is very, very small, less than 0.00001, right? So our conclusion is there's likely to be a difference. There is a difference in mean right wing length between area A and area B birds. The confidence interval suggests the difference is between 4.3 and 7.5 millimeters, with area A birds being larger. We can be 95% confident. Okay. What about area A and C? Well, let's do area A and C. So we've already got area A. We don't really need that other subset, do we? We've already got that one. But we could do area C, and now we could test between area A and area C. Okay, so our p-value here is larger, right? It's 0.12. So if there was no difference between area A and C birds in terms of average right wing length in the population, we'd expect to see a difference like in our data about 12% of the time, just due to random sampling. So our data are consistent with there being no difference between area A and C birds. This is confirmed with the confidence interval, right? Which sees the difference area A mean minus area C mean is between minus 1.6 and 12.5 millimeters. 0 millimeters, i.e. no difference, is an option. Okay, so our conclusion is area A and C birds are about the same, but area A birds are larger than the area B birds. What about area B and C? So area A, B, and C we've now got, so we can just do the test directly between B and C. And what do we see here? Well, again, our p-value is very large now, 0.9. So that's saying what we see could happen by chance, 90% of the time. It's a very frequent thing that would happen. So our conclusion would be our data are consistent with the sort of random variation we'd expect if the area B and C birds were similar, had the same mean right wing lengths. This is confirmed with the put the p-value in. This is confirmed with the confidence interval that again says that 0 millimeters difference is a possibility. It could be from minus 7.5 to 6.6. So we have an inconsistency here, right? Right, so we know that A birds are bigger than C birds, bigger than B birds, but A and C birds are similar, and B and C birds are similar. Right, how can this be? Right, so we know that A birds are bigger than B, right? B's the same as C, so you'd expect that A would be bigger than C, right? B and C are the same, A is bigger than B, so A should also be bigger than C. But we've actually found that A and C were similar, so we have some weird consistency. And so this sort of inconsistency can happen often when we have multiple, i.e. more than 2 groups to compare, as the only thing that we can do with t.test is pairwise comparisons, right? We can't compare all 3 at once, we just have to compare, so we've compared A with C and A with B and B with C, and all of those pairwise comparisons can result in inconsistencies. And you can, when we look at the plot, we can kind of see why, right? So if we go back and have a look at this plot here, what we actually notice here is that C is between A and B, right? So A is the larger group, B is the lower group, and C is sort of halfway in between. And it's made worse because C doesn't actually have that many birds in it. Okay, area C only has 13 observations. So only 13 birds in area C. So we just don't have much data to be able to say that B and C differ, or that A and C differ, just because we don't have much data in C. But we do have lots of data in A and B, so we can say that they differ. Right, so the only thing we conclude is that A and C could be the same, B and C could be the same, but we do have lots of information to tell the difference between A and B. So we get this inconsistency whenever you have multiple groups, basically, right? There's the possibility for inconsistency. And it's just made clear here because C was so small. Okay, so this is happening as A and B have lots of information, have lots of observations. So the standard errors, so the uncertainty in the average for A and B birds is small. Right, so if you're just using area A and B birds, because the uncertainty in the mean for area A and the mean for area B are small, we can tell them apart. But area C has few observations, right? 13 of them. So the uncertainty in the average right wing length for C is large. So we can't really tell with much confidence whether the C birds are different to either A or B, as we're too uncertain about what their average is. Later on, we'll look at how we can solve this issue. Are any of the areas different, or are they all the same? right? So we'll look at a slightly different hypothesis, which isn't just, pairs of them the same, but asking the more general question, are any of them different, or are they all the same? Okay, so we'll see how to do that once we go into linear modeling. Okay, and so essentially we're going to be starting linear modeling now by looking at a new data set on donkeys. So we'll run this code block here, which reads in data on donkeys. Okay, and we've done a plot of to see whether there's a difference between the male and female donkeys, and we see that there isn't, is there? Okay, not much difference between the body weight between the sexes, but there is a strong relationship between body weight and heart girth, and there'll be relationships with the other variables that we have in this data as well. If we have a look at donkeys here, then we've got umbilical girth, length and height as well, and also age. And we'd expect all of those things to affect the body weight, wouldn't we, of a donkey, right? The measurement dimensions are going to affect the body weight. Okay, so from the plot, it seems male and female donkeys have similar average body weight. There's a fairly strong increasing relationship between heart girth and body weight. Okay. So let's do a test now, a hypothesis test, to see if there's a difference in average body weight between the sexes, right? So we're going to be doing body weight in terms of sex from the donkey data. Okay, so what do we see? Well, the p-value is large. .4, which suggests that any difference we observe in our sample could just arises fairly frequently due to sample variation when there is no difference in the population. Between the sexes. The confidence interval confirm this, suggesting that females could be up to 7.2 kilos lighter than males, or up to 2.9 kilos heavier than males. 0 kilo difference, i.e. the same, is an option. Okay. So with hypothesis tests, we're always thinking about, we take a sample, we think, is the sample just something that could happen by chance? So is the sample consistent with the type of sample-to-sample variation that we would expect? Okay. And the p-value is what quantifies that. So small p-value tells you that there is a difference. The difference that you're observing in your data are unlikely to arise due to that sample-to-sample variation. So just at the end here, what we're going to do is we're going to go back and have a look at the scatter plot, and we're going to think about what would happen if there was no relationship between these variables. So clearly we see a relationship here, right? As heart girth increases, the body weight increases. If we had no relationship, then what we'd expect, I think, is that the body weight wouldn't change, would it, when heart girth changed? So as you changed from low heart girth to high heart girth, if there was no relationship between these variables, you'd expect the body weight to stay the same. Right? So what you'd expect is that you just have scatter all the way across and no evidence of trend. Okay? And so what you'd expect is that a flat line would fit the data, right? A constant line of body weight, because your heart girth wouldn't tell you anything about body weight, right? So no matter where you are on the heart girth axis, it's not going to change what you think about the average body weight, right? So okay, so if there was no relationship between two numeric variables, what we'd expect is that as we change the x variable, there'd be no change in the average of the y variable, i.e. a flat horizontal line would fit the data on a scatter plot. So in this case, we don't have a flat line at all. A clearly increasing line. So there is a relationship between heart girth and body weight, which is kind of what you'd expect, right? I mean, you know, if I just asked you before you'd even seen the data, if a body weight of a donkey is going to change by you know, the measurement around its heart, you would say yes, right? Bigger donkeys are going to weigh more. So that makes perfect sense. So we could formally test this by checking what the slope of that line is and comparing it to what we'd expect the slope to be due to random sample to sample variation under the hypothesis of no relationship. Right, so what we'd expect if there was no relationship is the slope should be 0, but just due to chance it might be slightly positive or slightly negative, right? It might be going up a little bit or going down a bit. It'll jump around a bit from sample to sample, but that's what we'd expect. We'd expect it to be relatively flat. In this case, it's clearly not flat, right? There's strong evidence that it's not flat here. It's definitely going up. Okay, so we'd expect our p-value here for the slope to be really small because it's you know, super inconsistent with it being flat. Okay, we'll see how we do that in lecture 6.